All right. Good day, team. Whenever you're watching this, I don't know, morning, noon, or night, welcome back to Miss Bowman Rambles On for a long time about some awesome mathematics. We are going to be going through the Unit 1 Day 4 notes. It's going to be covering section 2.3 from our book on continuity. So we're going to be defining, doing some definitions today, some explanations today, and kind of really delving deep on what does it mean to be a continuous function. So first we're going to kind of go through what you've done in the past with continuity, because we've done it a little bit in Math 4, so we're just going to kind of refresh that. Throughout this lecture, I'm going to be asking you to pause and try problems. You have the guided notes packet, so we're on the day 4 if you want to follow along and kind of do those examples. If you're doing this on your own and making stuff, remember you can pause me anytime. That's the glory of these recordings, probably the only benefit to these recordings in my mind, but we're here. So we're going to get started. What is a continuous function? So in the past, we defined a continuous function to be a function that has no breaks, that you can kind of like start the function by drawing it with your pencil down and draw the entire function without ever having to lift up your pencil. So that's kind of the layman's definition of continuous. So what I want you to do is kind of pause me, and given this graph of f below, I want you to find all the places where the function is not continuous. And then by looking at those places, we're going to be able to kind of define in a way with more integrity of what it means to be continuous. So pause me and just kind of make a list of all the x values on this function where the function is not continuous. Okay. Pause me. All right, now you should be unpausing me, and I'm just going to make a list of those places. So the function is not continuous at x equals -3, -1, 1, 2, and 4. Now, if I were to ask you where the function is continuous, the function is continuous at an infinite number of places. All of the places within that domain, except for the ones that I listed, would be places where the function is continuous. So x equals 0, x equals 1.5, x equals 3, x equals -3.772. Like all those places the function is continuous. The list of where it's not continuous is a lot shorter. So we have those 5 places on the graph, and I'm just going to kind of highlight them so we can see those places. And then we're going to talk about why they're not continuous at those places. So if I'm looking at that and I'm trying to decide why the function is discontinuous there, well, I'm going to look at like what's happening on the graph. So if we look at -3, if I'm traveling along this function, I'll do it in purple, I have to lift up my pencil and make a point over here and then jump back down to where the road is or where the rest of the function is. So if I think about what's happening at -3, there's a little bit of a jump that happens, an instantaneous jump that happens to a point that causes our problem to happen. Now, if I look at -1, we call this a jump discontinuity. There's a place where I'm heading towards -1 and it looks like I'm intending to go to a height at 1, but then once I hit -1, I'm jumping up to a height of 2, and that's where the actual height is. So there's a disconnect between what the actual height is and what the function was intending to go to on the left. And I'm being really, really, really particular about that language so that you can see that. And you can see that happens again at 1 and at 4. And then at 2, it looks kind of like the same case at -3. So what can we say has to be true in order for something to be considered continuous? There are 3 parts to really concluding that a function is continuous at a given x value. So we can say a function. Now, from here on out for the rest of the year, I'm probably going to use this little fn to represent the word function because I'm a little lazy. Is continuous. Continuous at x equals c. So now remember, most times in a graph, it's going to be continuous in a lot of places and discontinuous at just a finite number of places, if at all. So if we're looking at those places where it's not continuous, it's going to fail one of these 3 parts. So I'm going to say if the first condition, I'm going to try to do a Roman numeral here, guys, but it's not going to work. I often think aloud a lot, so I'm sorry if I'm thinking aloud and you're like, this teacher is crazy. Remember, this is a judgment-free zone, so don't judge the fact that I speak my thoughts aloud a lot. I'm always wondering, what are you thinking when I do that? But, you know, it is what it is. I'm saying this to avoid of space. It's actually July 30th, if you really want to know the truth, when I recorded this lecture. So here we go. A function is continuous at x equals c if f of c exists. So what that means is that the function has to be defined at that place that we're looking at to be the first condition that we have a continuous place. There has to be a point there. So this in layman's terms means that the point exists. The function has a value. So if I'm looking at x equals 1 and I plug 1 into the function, I'm going to get something out. So if you think about like asymptotes, those are places where the function doesn't have a value, where f of c does not exist, or holes where f of c does not exist, those type of places. You can think of our little like absolute value of x over x, a little step stool graph that I'll refer to a lot. It has like holes at 0. So those are places where the function is undefined at the point. And so we're going to say it's discontinuous. So if there's no point, it can't be continuous at that point. Get it? Because no point can't be continuous at the point. So it has to be a point. So that's like base level. Now the second thing is that in order for something to be considered continuous, we have to show that the limit as x approaches c of f of x also exists. So what that means is the intended height I'm going to from the left and the intended height I'm coming to from the right has to be coming towards the same height. So there has to be a general limit. So if we go back to our first picture, at x equals 1, right here, the limit coming from the left is 2 and the limit coming from the right is 0. So this limit does not exist. And if the limit doesn't exist, we know that we're not intending to go to the same place, that we're going to be jumping on the graph, and therefore it would be discontinuous. Now, most people are going to be like, oh, that's totally good enough. As long as there's a point and a limit, then the function's going to be continuous. Now, there is a third condition. So first condition, you have to at least show, oh my gosh, something's happening. At least show that the limit exists and that the point exists. Now, the third part of continuity is going to be that the limit as x approaches c, the intended height of the function, and the actual height of the function are the same. So there's got to be a point, there's got to be a limit, and they have to be the same value. So going back to that example, if you look at x equals -3 here, is there a point at -3? Yes. F of -3 is 1. Was there a limit at -3? Yes. The limit as x approaches -3, the intended height of that function is -1. But this function is not continuous because the actual height here and the intended height where it looked like it should have gone are not the same. Whereas if we look at something like x equals 0, which I'll highlight with a little purple circle right there, f of 0 is 2. If I look at what the limit is approaching 0, the intended height is still 2. So the limit as x approaches 0 of f of x is also 2. So because the point is 2 and the limit is 2, they are the same. Therefore, we can say that function is continuous at x equals 0. So it's going to be continuous, again, at an infinite number of places. But it's going to be discontinuous at one place, or at a finite number of places. So let's go over the types of discontinuities that you'll see in a graph. And you kind of saw a lot of those. Well, you saw 2 of those. I'll take that totally back. You saw 2 of those in that last example, but I'm going to kind of go through. Now, there's really 2 types of discontinuities, what we call removable discontinuities and what we call non-removable. Removable means I can fix the function and make it continuous. So that's what removable means. Non-removable means we're just like crap out of luck. Like there's no way to make that function continuous. It is what it is. So a removable discontinuity is called a hole. And actually some books don't even call it holes. They just call them removable discontinuities. So here's an example of a graph that has a removable discontinuity. Now you're like, well, I can see it's discontinuous. What condition does it fail? Well, it fails the fact that there is no point. Or it could be the fact that the point is up here or down here, someone other than the actual height. So that's an example of a removable discontinuity. And it's called removable because in order to make this function continuous over its entire domain, all I have to do is plug up the hole. That's adding 1 point to a graph. That's possible. I can add 1 point to a graph. What I can't do is change an infinite number of points, which we'll see here in a second. So the next example is a jump discontinuity. So for example, our little step stool graph. Again, I'm going to refer to this graph over and over again, which is absolute value of x over x. That graph, the limit as x approaches 0 from the left is -1 and from the right is +1. The limit does not exist, therefore it's not. Now, in order to make this continuous, one, I'd have to add a point at 0 because there's not even a closed circle at 0 on this graph, so that's like completely screwed. So one of these would have to be closed, but I'd have to move this entire ray down to match the other one. There are an infinite number of points here. There is no way I can change an infinite amount of points without changing the function and its characteristics, okay? I can add 1 point to a function. That's easy to do. I cannot change all the points on a line. Okay. Third type is what we call an infinite discontinuity. So an infinite discontinuity is going to be a fancy way of saying an asymptote. And it's called an infinite discontinuity because at that x value, 1, the function's undefined, but 2, the limit of that function from either side is approaching 1 of the infinities. So an infinite discontinuity, we also call it a vertical asymptote, is a place where the function is discontinuous. Now, if you don't remember the words infinite discontinuity, you just tell me there's a vertical asymptote, and that's why, I'll totally accept that. Like, that's totally fine. It's just that the book in the AP exam might use the language of infinite discontinuity. I just want you to be familiar with it. Now, this fourth type of discontinuity is the craziest type, and I'm laughing because what you'll see, it's called an oscillating discontinuity. Now, you might have seen that word before. You may not have. It's a weird word. Oscillating, just like fans oscillate because they keep going around and around and around in a circle. Oscillating functions are functions that kind of like bounce from up to down. So think y equals sine x. Like the sine graph goes up, down, up, down, up, down, up, down forever. That's an oscillating function. An oscillating discontinuity, an example would be y equals sine of 1 over x. So sine of 1 over x, what happens is, it's like I'm a regular sine graph. I'm a regular sine graph. I'm a regular sine graph. And then my oscillation starts speeding up. And really, what's happening is at this point in the graph, I'll change my color, this point in the graph, it's oscillating so fast that I can't actually tell where it is. It's kind of like a little electron. It's just flying around there, and I can't see at 0 what's happening. It's kind of like a WTF situation. Like, what the heck is actually happening there? I can't tell. It's just oscillating too fast. That's probably the one and only time you'll see that discontinuity, but I wanted to throw that out there because it is one that, you might see, so we should be ready for it. Okay, so now going through continuous and discontinuous functions. 90% of the functions that we're going to be dealing with are going to be continuous over its entire domain. So if the domain is from -infinity to infinity, it's continuous at all those places. If the domain is 0 to infinity, like the square root function, it's continuous over its entire domain. There are some functions that will have exceptions, and rational functions are those that you've graphed before in Math 4 that are going to have discontinuities. Now, if I ask you to remove a discontinuity, one thing you need to realize is you can only remove holes. That is the only type of discontinuity that is removable. So I would have to identify where, if this function has a hole, and if so, what is the intended height of that hole? And once I figure that out, then I can remove it by plugging the hole. And so we're going to do that by adding a point to the whole. So if we look at little f of x here, I'm going to factor out my f of x because I always are just in the habit of factoring these rational functions. And it's already telling me where the whole is, but I just want to show you how I'm going to identify that that's a whole based off of what I know about rational functions and what you may have forgotten about rational functions that we're going to go over. One way you can identify a whole. So one way to identify a whole is just to plug in 2. If you plug in 2 and you get 0 over 0, that's your clue. Remember, that's that indeterminate that there might be a hole in the graph, okay? If you get a number over 0, that is your clue that there is a vertical asymptote, which is what we talked about last lecture, a vertical asymptote. So if I were to plug in 2 here, I get 2 minus 2, which is 0, times anything is 0. 2 minus 2 is 0. If I times anything, it's 0. I get 0 over 0. That's a good clue that it's a whole. The other way you can recognize it is the factor that cancels out or reduces out of a fraction is going to be where the whole is. So if x minus 2 is the factor that cancels out, then at x equals 2, there would be a whole. So what we want to do here is we want to identify what is the limit as x approaches 2 of f of x. And the reason I factored that is because by doing so, I've simplified the function and I'll be able to find the limit. So the problem with a hole in a graph is that there is no point where we want it. So what we're going to do is we're going to figure out what the limit is because that's the intended height of the function. And if I find out what the limit is, then I'm just going to put a point where that intended height is to make an actual height meet an intended height. So if I were to plug f of x into my simplified function, I would end up with 2 plus 3 over 2 plus 2, which gives me 5/4. So that tells me graphically, if I were to graph this part of the graph and I got to 5/4, that's where my hole is. So it's at an intended height of 5/4. So what I'm going to do here is now I'm going to rewrite this as a piecewise function. That's supposed to be a curly bracket, but it didn't work out. So I'm going to have x squared plus x minus 6 over x squared minus 4, where x can't equal 2. Actually, I'm going to take that back. I'm going to write the simplified one because it's just less to write. So I ended up with x plus 3 over x plus 2, where x can't equal 2. And then I'm going to add a point in my piecewise function. So my point is going to be at x equals 2, I want a value of 5/4. And that is removing the discontinuity. All you're doing is now making your function a piecewise function where you're adding a point. And that's the only thing you're allowed to do to remove. Okay, so for instance, this one, extend the function h such that it is continuous. So if I look at this function, it's going to have a discontinuity here. What is the discontinuity going to be? Well, if I plug in 4, I get 4 minus 4 over root 4 minus 2, which gives me 0 over 0. That's my clue that this is a whole. And that should say whole. There we go. Okay. That I can now know that I can plug that hole and extend the function so that I extend the function to make it a piecewise so that now it's continuous everywhere. Now the question is, how do we do that? This is a harder example. I'm going to say pause me, maybe try it, and then come back after you've tried it, and we'll talk about it. This is a really tricky one. You might have seen it in the day 2, but if not, just give me a pause. I'm going to take a sip of water. And now we'll go back through it. So here, what I'm going to do is I'm going to find the limit as x approaches 4 of this function. So I'm going to go ahead and write h of x's function expression in here instead of saying h, only because I want to manipulate it. So I already know if I plug in 4, I get 0 over 0. So that tells me that, like, I know I have a hole. Now the question is, how do I rewrite this function in order to figure out what the height of the hole is, or what to find out what the actual value of the limit is, because that's the same thing in this case. Now, there are a couple of different ways that you can approach it, and we'll probably talk about this problem in class and all the different ways that you did in your homework when you pause me, because that's what you're supposed to do, and tried this problem on your own. Okay, so remember, you're always pausing me, trying your problem on your own, and then kind of going from there. Now I'm going to go through the longer version of this just so you can see it, but anytime you have a radical expression within a fraction, one method for solving it when there's an indeterminate is to use what we say is the conjugate. So that was one of the indeterminate strategies we had that we didn't get to practice. So I wanted to make sure we practice this in a lecture series so that you can kind of see it. So what I'm going to do is I'm going to multiply this expression by root x plus 2 over root x plus 2, because that is the conjugate of that part that has a radical. Now, here's my advice to you. What I'm going to do is I'm not going to distribute that top. I'm going to leave it as the quantity of x minus 4 times the quantity of root x plus 2. The bottom, however, I am going to distribute. So I have root x plus root x, which is x. Root x times 2 is 2 root x. Negative 2 root x. And then negative 4. So now notice that I'm keeping my limit notation because I haven't plugged in 4. All I'm doing is rearranging the expression. So I'm just going to keep going with that. Usually we use conjugates when there's a radical. Actually, we don't. It just could be anywhere. Anytime there's a radical, use a conjugate. If I simplify that, these middle terms cancel. So I end up with x minus 4. Now, if you did it right, you should notice that we have a common factor that I can reduce it by. So now, if I reduce my fraction, I have the limit as x approaches 4 of root x plus 2 over 1, because that's all I have left on the bottom. So now, if I plug in 4, I get root 4 plus 2, which ends up being 2 plus 2, which is 4. So if the limit is 4, then that's the intended height of the function there. So I'm going to add and extend this function. So now I'm going to make it a piecewise. So I have my original function when x couldn't equal 4. And then I'm going to add the point where the intended height was. So if my intended height is 4, I'm going to add a point with a height of 4 at x equals 4. And I have now extended my function, and I've made that function continuous. All right, moving on. The rest of it we're going to kind of look at is how do we tell if a function is continuous if it's a piecewise function. Okay, now in order to do a proof in calculus, you got to go back to the definition. So I'm just going to go back to the definition real fast, which was there has to be a point, there has to be a limit, and the point and the limit have to be the same. So in order to show this, I'm going to say, okay, is there an f of 2? And I'm really just testing the break in the domain because I know 3 minus x is a linear function. It's continuous everywhere. X over 2 plus 1 is also a linear function. So the only possibility that could happen here is that I have a jump at 2, and that's what I'm going to test for. So if I plug in 2, I'm going to plug it into the function that includes 2 in the domain, and I end up with 2. Okay. Now I need to prove the limit exists. So I need to find the limit as x approaches 2 from the left of f of x, and the limit as x approaches 2 from the right of f of x. And we're going to find both of those limits. So if we look here and we're trying to find those limits, if I want to approach 2 from the left, I'm going to use the domain where x is approaching 2 from the left-hand side, so x is less than 2. I'm going to find the intended height here by plugging in 2 into that expression, and I get that the left limit is 1. Now the right limit is going to be the ones that are greater than or equal to 2, so I'm going to plug 2 into that expression, and I end up getting out 2. Now, I'm going to look, does the left limit equal the right limit? If the answer is yes, then the limit exists. If the answer is no, then the limit does not exist. So I'm going to say, therefore, which you can use 3 dots if you're feeling fancy, the limit as x approaches 2 of f of x does not exist. And that's because the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x And then I can say f of x is not continuous. At x equals 2. And I apologize again. Sometimes the surface just kind of lags, so it makes my handwriting look atrocious. Okay, so moving right along, let's do a little bit of a different example here of how to do continuity. I'm just kind of taking to see how much we got left. Okay, moving great. So creating continuous functions. So if I wanted to make it so a function is continuous, the AP exam, by the way, loves this type of question. So here we're going to say find a value a for a so that the function f of x is continuous at x equals 3. So if I want to do that, then I want to find where the intended height and the actual height are the same. Now I can see that one of the branches includes 3, which means that the right limit and the actual value of the function are the same. So I'm going to focus on making the limit exist. I want the limit as x approaches 3 from the left of f of x equal the limit as x approaches 3 from the right of f of x. So if I plug 3, and notice this notation here, this is my proof. Without this notation, it means nothing. So you really need to include the limit notation of what you're doing. It's explaining why you're doing what you're doing without having to write a bunch of words. So if I find the limit from the left, I get 3 squared, which is 9, minus 1 is 8. So on the left side, the limit is 8. If I plug in 3 for x on the right side, I get 2a times 3. So now I end up with 8 equals 6a, which means a is equal to 4/3, or 8/6. I just reduced it in my head. So as long as a is equal to 4/3, then the left limit and the right limit would be the same, and the actual value of the function would match the limit because it's attached to it anyway. Okay, so that's kind of the idea of continuity. Now, why continuity and proving continuity is important is because continuity ends up being a condition for a lot of things to hold true. And if we can prove that a function is continuous over its domain, then there's a lot that we can conclude about that function. And there are going to be 4 major theorems that we study throughout the course of calculus. And we're actually going to do the first theorem right now. You know, week 2 of school, we're just jumping into this first theorem. And so we're going to talk about the hypothesis of the theorem, which are the conditions that are necessary for you to use the theorem, and then what the conclusion of the theorem or what the theorem allows you to say. Okay, so the first theorem that we're going to be studying this year is called the intermediate value theorem. And there was a moment in Math 4 for like 3 seconds that you did the intermediate value theorem. But I don't expect you to remember that from Math 4. So we're going to go through it again and talk about the hypothesis and the conclusion, and then kind of how do we use this theorem and what does this theorem allow us to conclude about a situation or about a function. So the hypothesis of the theorem, this is like some science stuff here. The hypothesis for us are going to be the conditions necessary for the theorem to work. And I'm going to say for theorem to always work. This theorem is what is known as the intermediate, which if you think about that word means middle, value, which is height, theorem. And a lot of times we're going to refer to it as IVT for intermediate value theorem. AP exam does it as well. So you can always refer to things as IVT for them. Okay. I like to call this the guaranteed height theorem. Okay, so the hypothesis is what's necessary for us to make a certain guarantee about a function, and the conclusion is what the guarantee is. Now, if the hypothesis of a theorem is not met, it doesn't mean that the conclusion won't hold true in any case. It just means that we can't guarantee it. So this is all about the guarantee. If I could spell, I don't think that's right. Guarantee. That looks right. This is what happens when we guarantee stuff, okay? So the intermediate value theorem says, the hypothesis, if a function, so there's my little shortcut, is continuous. Let me try. Continuous. So now do you see why we talked about continuity? Is continuous on A to B. So that really just means a closed domain. Okay, so if a function is continuous on a closed domain, so that's a condition that has to be true. We have to have a continuous function and it has to have endpoints. So if you want to make yourself a note that this means closed domain. Now you're like, okay, that's cool, but what are we going to be able to conclude or guarantee about the function if this condition holds true? So here's what the immediate value theorem says. Now, the way the book writes it is really confusing, but I want to write it that way, and then I'm going to try to explain it to you in like plain English so that you understand what the conclusion is. So if a function is continuous on A to B, then there exists a C between A and B let's just say C. There exists a C between A and B such that f of C is between f of B and f of A. Okay, so there exists a point C where C is between A and B such that f of C is between f of A and f of B. So in layman terms, what this means is if a function is continuous on a closed domain, then we can guarantee all the heights exist between the heights of the endpoints. So it's not about the x's here. This is like the guaranteed height theorem. So we can guarantee that every height between the heights of the endpoints exists in that interval. So what that says is if a function is continuous on a closed domain, and let's say one endpoint is at a height of 1 and the other endpoint is at a height of 5, that tells me that all the heights between all the values of the range has to go from 1 to 5 continuously. So there has to be a point where the height is 4. There has to be a point where the height is 3.2. There has to be a point where the height is 1.7. Okay, so that's what intermediate value theory says. It says if I have a continuous function on a closed domain, I have to hit all the heights between the heights of the endpoints. Okay, the continuity guarantees it. Now, could I have a discontinuous function where all the heights are still hit between the heights of the endpoints? Yes, but it's not a guarantee. And what theorems in mathematics do is they guarantee things. So we're going to kind of look at some applications of intermediate value theorem, just a couple, look at a graph and kind of delve into it. We'll probably, again, talk about this more in lecture. Okay, so here's an example of where intermediate value theorem might be seen in response to like an AP exam or in a theoretical way. Let's say I give you a table of values of x and f of x, and I tell you that f of x is continuous. So I'm going to tell you that f of x is continuous from -2 to 2. Okay. Is the hypothesis satisfied in this condition? Yes. The hypothesis is that we have continuity on a closed interval, and we do within this table. Now, the conclusion is all the heights between the heights of the endpoints have to exist. Another way to think about that is there a value of x where f of x has to equal 0? So looking at these heights, could we guarantee that this function has a height of 0 someplace. So pause me, think about it. Would this function have an x-intercept somewhere in this interval? Pause me, unpause me. The answer to this is yes. 2 places. Between 9 and -6 would have to cross 0, and -8 to 6. Now, could it happen between -6 and -8? Yes. I don't know what's happening between those points, but can I guarantee it? No, and that's the difference here. So I'm going to say yes on -1 to 0 because f of 0 is less than or equal to 0, and that's less than or equal to f of -1. So what that's saying is 0 is sandwiched between -6 and 9. So you can think -6 was f of 0, and 9 was f of -1. Okay, and 0 is between those two numbers, so 0 has to hit, the function has to have a value equal to 0, or a solution of x equal to 0 in that interval. And then I'm also going to say on 1 to 2, because f of 1 is less than or equal to 0, which is less than or equal to f of 2. Okay, so here's the domain on which it has to happen. Here is my reason why. Now, on the AP exam, if you want to say yes, you have to say this first. The only way we can guarantee that it has to hit 0 and it doesn't just jump from 9 to -6 is if the function is continuous. So you're never going to say this is because of intermediate value theorem. Like the IVT is never a reason why something happens. The reason why it's happening is because the function is continuous. The hypothesis is the reason why we can state the conclusion. The name of the theorem is just the name of the theorem. It is not a reason, okay? I'll probably have to say that 17 more times, which is totally fine. Okay, so look at this one. I want you to attempt it on your own. Pause me, and then we'll kind of go over it. What value would k have to be to ensure that the value f of x equals 3/2 happens at least 2 times? There's some bad grammar in here. 2 times, 1 time, and 0 times. So think about it, pause me, unpause me. Okay. If I want to make sure f of x has a solution of 3/2 2 times, I always kind of have to think about what this picture looks like. So at -5, I'm at a height of 0. At -1, I'm at a height of 1. At 7, I'm at a height of 1, and I'm at a height of 0. And here's y equals 1.5. So I want to make sure that I can hit this horizontal height 2 times. Well, the only way that can happen is if k is bigger than 3/2. Because if I make this point at 3 above 3/2, then it's going to have to cross through to get to it and cross back down, and it's going to hit 2 times. So any value that's higher than it will guarantee that it hits it 2 times. If I wanted to hit it 1 time, I could guarantee 1 time by making k equal to 3/2. Okay, now could it hit more than that? Yes, we don't know, but we can guarantee that it hits at least 1 time. Now, if I want to make it so I can't guarantee it, I would just make it less than 3/2. If this doesn't even show me 3/2, let's say I put 1/2 here, then I have no idea if this ever hits 3/2. So as long as my k value is below that height that I'm trying to guarantee, then I'm never going to do it. And picturally, it'd be like this. Like if I went like that, then I would have like no idea if it actually hits it or not. It still could, but again, the theorem is all about guaranteeing stuff, not about what could or could not happen. Okay, so let's look at 2 more examples of IVT, and then that'll be the end of day 4. And then we'll talk about some more in class. So what, if anything, does IVT say about the following? Explain. I was 23 miles from home 2 hours ago, and now I'm 2 miles from home. So what could I say about IVT? Well, I can first make a statement. Distance is a continuous function. Okay. Since it is, I know at some point but in my 2 hours, I was 15 miles from home. Okay. So since distance is a continuous function, I know that at some point in my 2 hours, I was exactly 15 miles from home. I could actually say I was exactly 22 miles from home, 21 miles from home, 20 miles from home. I can guarantee any mileage between 2 and 23. So any miles between 2 and 23 has to exist because the function is continuous. So notice that I didn't say because of IVT. I didn't even write IVT anywhere in my explanation. The only reason why is because it's continuous. So let's play with one more idea about IVT, and we'll look at this graph here. First, there's like this weird, we're just going to ignore that. Okay, so here I have this graph that is defined between -8 and 15. Okay. Question A. Actually, I want you to pause me and answer these 6, take about 5 minutes maybe, answer these 6 questions. Then unpause me and we'll kind of go through it together. Again, we'll probably talk about this one in class as well because this can tend to be a tricky one. So where is f discontinuous on the interval in -8 to 15? So where are the discontinuities at x equals 0? What condition does it fail? There's no point there. And at x equals 5, what condition it fails? It does have a point there. It does have a limit there, but they are not the same. So it fails the third condition. Okay. Does the hypothesis of IVT apply from -2 to 3.5? So I'm just going to highlight with my highlighter, and I'm going to use cyan because why not? So -2 here to 3.5 here, that's this part of the function. Does the hypothesis of IVT apply? No. Whoa, I don't want it to be yellow. Let's try that again. No. Why not? Not continuous. That's the hypothesis. I almost wrote hypothesis. Not continuous. Okay. So again, the hypothesis of this is that the function is continuous. So do the conclusions of IVT hold from -2 to 3.5? No. It's an automatic no because it's not, it doesn't, the hypothesis isn't met. So if the hypothesis isn't met, we can't guarantee that the conclusion is met. Now, the other thing I can think of is this is no, because if I look here, -2 has a height of 6 and 3.5 has a height of like 14. And the conclusion would say every value between 6 and 14 is hit at least once, which I can see isn't true because I don't have a height of 9. So because it jumps over 8.59, 9.99, like all these values don't exist. So the conclusion does not hold true. F of x does not equal 9 would be my reason. Okay. Does the hypothesis of IVT apply from -2 to -1? So now I'm just looking from here to here. So I don't know why it keeps moving down. So now I'm just looking at this part of the graph from -2 to ooh, back that train up. There we go. -2 to -1. So I'll do that kind of and make it blue. So I'm looking here. Does the hypothesis hold true? Is it continuous on that interval? The answer to that question is yes. So the hypothesis is true because it's continuous. So is the conclusion true? Yes, because it's continuous. So if we say yes to the hypothesis, we can have to say yes to conclusion. If we say no to the hypothesis, We could still say yes to the conclusion, but we can't guarantee it. And in fact, F says find an interval where the hypothesis does not hold true, but the conclusions of IVT do. And now this is the really tricky part. So we're going to look at this graph. So I want the hypothesis to fail, which means I want it to be discontinuous on an interval. And I'm going to go ahead and erase all my little marks. We have a fresh graph to look at. If it will stop moving down on me. There we go. Okay, so I'm going to try to pick a certain part of this graph that is discontinuous, but where all the heights between the heights of the endpoints that I choose are hit at least once. Okay, now I'm going to choose a really confusing. There are an infinite number of answers that you can have here. For instance, I could choose from -8 to 15. I could go the whole length of the interval. And you're like, but 9 doesn't happen. But remember, the conclusion is that the heights between the heights of the endpoints happen at least once. So if I pick -8 and 15 to be my interval, then I have to look at what the height is at -8, which is a height of 0. And what the height is at 15, which is like -5. I just think I drew it real crooked, or -6. Now I'm going to ask myself, do all the heights between those two heights fit within this interval? So if I look at this interval, yikes, guys, I'm sorry. Let's try that again. So if I look here in this window, so I'll go ahead and draw some like window markers. Do all the heights happen between those two x values? And the answer to that is yes, right here. So if I look at this part of the graph, these are the heights that I kind of highlighted in pink. These are the heights that IVT would guarantee, the heights between the heights of the endpoints. All of these heights in the middle are outside of the range of the exact endpoints. Now they're happening and not happening, doesn't matter. IVT guarantees the heights between the heights of the endpoint. So the only thing I'm trying to guarantee is between 0 and -5, which all of those heights happen. So that's one interval. Another interval I could pick, let me go ahead and erase that. There we go. So let's pick another interval. So one interval was -8 to 15. Okay. What if I chose the interval from, sorry, it keeps moving down on me, from x equals 1 to x equals 10. Or whatever that is, x equals 10.5. Okay, no, it's 10. So if I go from 1 to 10, the hypothesis fails because it's discontinuous at 5. But if I look at what f of 1 is 11. And f of 10 is 11. Do all the points between 11 and 11 exist on that closed domain? Yes, because they're at the endpoints. And if the endpoints, all we can do is say between 1 and 10, there has to be a point with a height of 11. Is there a point with a height of 11? Yeah, at 1 and 10. So that's another one where it could work. So I encourage you to try to find some more and play around with this, because what happens is people will pick like these two intervals and they'll be like, well, it doesn't hold true because there's no 9. But if you look at the points that you pick, you're guaranteeing the heights between those two heights. So you're not guaranteeing all the heights between those two x's. You're just guaranteeing the heights between those two heights. So it's all about the value of the function and the heights. So try it for some homework. I'll see you in class. And that's all I got. So have a great day.